Hi everyone, this video is for 5-5, which is trapezoidal rule. So it's similar to the Riemann sums that you did in 5-1, but it's just using basically a different shape to find the area under a curve. So here's just a little reminder. Some of these notes I filled in ahead of time, so if you want to pause the video and add these to your notes, you can. But this is just a reminder of what a trapezoid looks like and how we find the area of a trapezoid. So we have these two different size bases if you want to think about it. So you take the average of those bases and you multiply it by the height. So this is what it looks like when you take an area under a curve and you divide it into trapezoids instead of rectangles. And you can see in some cases it's a better approximation than a rectangle. So this delta x is the width of each trapezoid. This n is the number of trapezoids. And then this is your interval. You're integrating on the interval from a to b. So this is basically minusing your interval. So here in this picture, this point would be A, and this point would be B. So this would be your first trapezoid, your second trapezoid, your third trapezoid. The height of this first one would be what you get when you plug x sub 0 into your function. So that would be f of x sub 0. This height would be f of x sub 1, and so on. So if you think of each trapezoid, it's going to have an area, the base is going to be this distance right here, which we're going to refer to as delta x. And the way we find that is we take b minus a and divide it by the number of trapezoids that we're subdividing our shape into. And then the height of, for example, trapezoid 1 is going to be the average of this height and this height. So we take both those heights and divide them by 2. So you can kind of see how that ties into the area of a trapezoid. So these are our two heights. On our graph, these are heights, and this is like the base, the width of the trapezoid. So it gives you an area, which we use then. An area under the curve is a way that we approximate an integral. So an integral is an area under the curve. So we say the area from a to b of this function is approximately equal to delta x divided by 2. And then these are our two heights. So this is our base, and this is our height. This is our base, and this is our height. This is our base, this is our height. Okay, so the 2 here comes from that 2. Okay, let's keep going. Simplify this a little bit. So if you think about, I'm going to flip back to my picture again just to show you something. If you think about when we do this, we're going to be using this height twice. We're going to use it for the area of this trapezoid and the area of this trapezoid. We're going to use this height twice when we find the area of both these trapezoids. So that's what this note says here. It says, notice that all the function evaluations with the exception of the first and last are multiplied by 2. So the first one, if you kind of do some simplifying on that equation from the previous page, you'll see this height, f of x of 1, was used twice. F of x sub 2 was used twice. All the trapezoids in the middle, those heights are used twice. The ones on the ends are not used twice. So that's why when you have this, you have delta x divided by 2. So this is our a plus b divided by 2. And then the first and last heights, we don't multiply by 2, but everything in the middle, we do multiply by 2. So this is trapezoid rule. Your book does it similarly. This h is the same as the delta x that I used before. So that's your b minus a divided by n. And then there's the 2. This is your first height, second, third, fourth, so on. This is your last height. So first and last are not multiplied by 2. So A and B is the interval that we're dividing up into n subintervals, and this is where they say h, or you can also think of it, I like to think of it as delta x because it's the width of the trapezoid, is b minus a divided by n, and n again is the number of trapezoids we're dividing the area up into. Another way to think about this is we're taking the left Riemann sum and the right Riemann sum, those two heights, and dividing them by 2. Okay, so this is just to kind of show you, for example, pretend we were taking this function, this is very blurry, and say we were dividing it into 5 trapezoids. So our delta x, or our h, would be 10 minus 0 divided by 5, which would be 2. So this would be our delta x, or our h. So if we're approximating the area from 0 to 10 of this function, I don't know why I have this parenthesis in here, it would be, it's going to equal approximately h divided by 2, or delta x divided by 2, f of 0 plus 2 times, wait a minute, we're dividing it into 5 trapezoids, and they're each going to be 2. So let's see, our first one, so this would be where our first trapezoid is. So these would be our first height. So our first height would be f of 0. Our second height, actually this should say f of 2. Let me just rewrite this part. I think I was thinking it was going to 1. So our second height would be 2 times f of 2. Remember, all the ones in the middle, you multiply by 2. Our next one would go to 4 here. So this would be the trapezoid. So the next height would be f of 4. And then 6. So you'd have 2 plus f of 6. And then 8. And that would also have a 2 multiplied by it. And then f of 10 would just be plain old f of 10, not multiplied by the 2. So that's kind of an example of what it would look like. Let's look at an example here where they give us the function. This one, by the way, is in your book, but we'll go through it. So we're doing the area under the curve, x squared. We're using the trapezoid rule with n equals 4, so that means 4 trapezoids. And then remember, you could put this in your calculator. And if you do, you would get the exact area is this. Okay, so remember that's fnint x squared x 1, 2. So the integral of this function with respect to x from 1 to 2, you always put in this lower bound first. Alright, so let's figure out our h, or our delta x. So that's going to be 2 minus 1, b minus a, all over 4, because we're dividing it into 4 trapezoids. So that's going to be 1/4. So our integral is going to be from 1 to 2 of x squared dx, don't forget the dx, is going to be equal approximately to delta x, or h, so that's 1/4, divided by 2, and we're going to do f of 1 plus 2 times f of, so the first trapezoid is going to go, so each trapezoid is going to be 1/4 wide, if you want to think about it this way. So the next one is going to be f of 1.25, so 1 plus 1/4, plus 2 times f of 1.5, add another 1/4, plus 2 times f of 1.75, add another 1/4, plus f of 2, we're at the end. So I encourage you to sketch this if you need to, but basically the first height is at 1, the second one is at 1 1/4, the third one is at 1 1/2, The fourth height is at 1 3/4, and the fifth height is at 2. All right, so then if you put all this in your calculator, which I am not going to do, you get 2.3438. And remember, this was our exact, this is our approximate. So, not too bad. All right, let's look at another one. This is a little bit messier function. And what are we doing here? N equals 4, so 4 trapezoids. And we're approximating the area between 0 and 2 of this function. So sometimes the trapezoid approximation is represented with a capital T, means trapezoid approximation. Trying to get this in focus a little better for you. So let's figure out our h, or our delta x. So delta x, which the book calls h, is going to be 2 minus 0 over n, which is 4. So that's going to be 1/2. So our trapezoidal approximation is going to be delta x, which is 1/2, divided by 2. And we're starting at 0, so it's going to be the height at 0 plus 2 times f of 1/2 plus 2 times f of 1 plus 2 times f of 3/2 plus plain old f of 2. Remember the last one, we are not going to multiply by 2, first and last. So each one is going up by 1/2. So I was going to sketch it, but you can graph it and see. So we start at 0, we go to x equals 1/2, x equals 1, x equals 1.5, x equals 2. So then you would want to put all these numbers into your function. So if I put 0 into my function, I'm going to have e to the 0. And then if I put 1/2 into my function, I'm going to have e to the 1/2 squared. If I put 1 into my function, I'm going to have e to the 1 squared. And then if I put 1.5, I'm going to have e to the 1.5 squared. And then not the 2, so this would just be e to the 2 squared. Definitely, you're going to get a decimal for this one, so you want to put that in your calculator. I should have did probably, well, this is a trapezoidal approximation, so I might not need the approximation symbol. I'm kind of already saying it's an approximation. So this is the approximation that I got. Now, if you put this in your calculator, you should get 16.4526. So this is a pretty big over approximation. It still might be better than an LRAM or an RRAM. Hard to say. All right, now you're sometimes going to be given the function like we had up here. Sometimes you're going to be given these tables. So this one says, oops, hang on, oh yeah. This is example 3 in your book. So an observer measures the outside temperature every hour from noon until midnight. So that's 12 hours, recording the temperatures in the following table. What is the average temperature for the 12-hour period? So this is, so think of these as your, these are your x's, these are your y's. So this is your f of 0. This is our starting time. So this is your height at f of 0. This is your height at f of 1. This is your height at f of 2. So this is x, this is y. So 12 hours we're doing this for. So our delta x is going to equal 1 because we have data for each hour here. So think that's the width of your, each rectangle has a width of 1. So our trapezoidal approximation is going to be 1 delta x over 2, or 1/2. And then these are all our heights. So we can just think, all right, first height plus 2 times the second height plus 2 times the third height plus, I'm not going to write all these, I think you get the idea. I'm going to go all the way down to here, 2 times the second to last height plus plain old second to last height. Remember, that one we do not multiply by 2. Make that a bracket. Okay, and then obviously put all that in your calculator and you get 782 divided by 12. And this is going to be approximately 65.17 degrees. So this is hours. So this that we get is per hour, and we're going to divide it by 12. So that gets us our average. And if you look at those numbers, that average makes sense. So this one, it was 12 F values that they gave us, and then we were dividing it into 12. So the delta x was all the same. Now, that is not always true, that the width of the trapezoids are the same. So that's what's happening in this one. And these do come up. So you got to look closely at these trapezoids and make sure that the width of the trapezoids are the same. They are not always the same. Couple of interesting things about this problem. It says at time equals 3 seconds, a hot air balloon is 50 feet above ground. So this is a height. Write an expression involving an integral that gives the position. This is important, so I want you to start thinking position, take the derivative, you get velocity, right? Remember this? Take the derivative, you get acceleration. Because in this problem, what they're going to be asking us to do is to go backwards. So if we're going forward, oh, why does it keep doing that? If we're going forward, we're taking the derivative, right? d dx. When we go backwards, we're doing the antideriv or the integral. So in this problem, if we keep reading, write an expression involving an integral that gives the position of the balloon in feet at time equals 15 seconds. Use a trapezoidal sum with 3 subintervals. So this means n equals 3. Indicated by the table to approximate the position. So we're finding position. And what did they give us here? They gave us velocity. So we're given velocity and we need to go backwards to position. So that means we're taking the antiderivative or an integral. So our answer is not going to be feet per seconds, it's just going to be feet. We're finding position. Now if you look at this, we're dividing it into 3 subintervals. But if you look at these distances in here, they're not the same. This is 5, the difference here is 5, the difference here is 4, the difference here is 3. So it's not like the problem we just did where the differences between all the x values were 1. So these trapezoids all have a different width. So we're going to basically approach it like finding the area of 3 separate trapezoids. And we're also we're doing 3 trapezoids. And this is where they're going to be. So this is trapezoid number 1, this is trapezoid number 2, this is trapezoid number 3. So let's just think about finding the area of each of these. So think of each of them as a trapezoid. These are our heights, these are our widths, and then we're going to sum those up to approximate the integral. So if you just think, I'm just going to write it like this, trapezoid number 1, the heights are right here. So I'm going to take the heights, 30 plus 75, and then I'm going to multiply it by my width divided by 2. So my delta x over 2, which is going to be 8 minus 3 over 2. So that's going to give me the area of trapezoid number 1. So trapezoid number 2, here's my heights, 75 minus 45 times 12 minus 8 divided by 2. And trapezoid number 3, here's my heights, negative 45 plus 20 times, this is my width, 15 minus 12 over 2. So, right, these are my heights, and these are my widths. So you can think of these as your delta x. So the integral from 3 to 5 of v of t dt is going to be equal to approximately, this is 5 halves, times 30 plus 75, plus, this is going to be 4 halves, 75 minus 45, plus, running out of room here, 3 halves, negative 45 plus 20. So I'm not really doing the multiply the inside ones by 2 and the outside ones not, because I'm doing the area of each individual trapezoid separately. So when you put all this in your calculator, you're going to get 285. Now this is the distance. I'm just going to write this. This is the distance traveled from t equals 3 to t equals 15. So they said to approximate the position of the balloon at time 15. So this is how far it traveled from time 3 to time 15. However, if you go back to the first line, I guess this isn't traveled, this is height. I guess that's traveled. It started at 50 feet above the ground. So we want to take this and add the 50, and we're going to say that's the initial condition or position, however you want to think about it. Initial condition, initial position. So this is its height at time equals 0, right? We didn't have a velocity at time equals 0 because it wasn't moving then. But the distance that it traveled is going to be both of those together. So that's going to be 335 feet. Okay? Here's one for you to try. If you use trapezoidal approximation on this, you should get approximately 1.1169. That's your trap. And then in the calculator, it's 1.1114 on your calculator. Okay, that is it, I believe, for 5.5, is it not? Yes, it is.